Hi everyone, this is Tristan, and here's my transition metal video. So let's take a look here. Our presentation today is going to be about why the spectrochemical series gives different d-orbital splitting and thus different colors. So for this video, we're going to be looking at 6 ligands in an octahedral complex. And the splitting is going to look like this with our 2 Eg orbitals above and our 3 T2G orbitals below. And we're going to take a look at how when we move those T2G orbitals up and down, that changes the energy and then thus the color that we see, which is why we have that color wheel there. Our basic case above is going to be our sigma-only donor, and what we're going to see is when we have pi donors or when we have pi acceptors, those T2G orbitals are going to move up and down, and that's going to change our colors. So the first thing we're going to take a look at is the relationship between energy, wavelength, and color. So we can take our field here, the Eg and T2G, and what we're going to do is we're going to perturb it. We're going to move that up. And when that happens, that energy becomes smaller. Our E1 is smaller than our E0. Now on the top right, we have an equation here relating our energy to our wavelength. As we see that energy go down because it's inversely proportional to our wavelength, that wavelength is going to go up. Now down below in the bottom right, I have this color wheel, and at the E0, the initial energy, I had it pointing at around 575 or so nanometers. And since we made that energy smaller and wavelength bigger, that's going to rotate and it's going to point to around 700 nanometers. Now note that originally it was absorbing yellow light, and now that it's moved, it's now absorbing red light. Now we can do the same thing in the opposite direction. We can move that T2G orbital down. When we do that, it increases the energy. So as we see in our equation, that E gets bigger and that lambda inversely gets smaller. We're going to see that we're going from a higher wavelength, around 700, to a smaller wavelength, around 420. Whereas before it was absorbing red, now it's absorbing purple. So now we're going to see what that means for the color we see. So in this initial case that we talked about a minute ago, we have it absorbing yellow, which means we actually see the color purple. And when we increase those T2G orbitals, move them up, we see that when it absorbs red now, that tail is pointing towards green, and we see green. Same thing happens when we rotate it all the way around again, move that orbital down, increase the energy, decrease the wavelength, and since it's absorbing purple, its tail is pointing towards yellow, so we see a yellow complex. So now that we have that background in terms of color and wavelengths and energy, let's get into the ligands we'll be looking at. So the first ligands we're looking at is our sigma-only donors. So our example here is our NH3. It doesn't have any p orbitals to interact. It can only have a sigma interaction here. And this is what it looks like around our metal, our 6 ligands around there. And for the sake of this video, this is going to be our purple color, right, where that arrow is pointing at yellow. Now things get destabilized when we have pi donors. So here's an example of a pi donor, this iodine, and it has these p orbitals with these lone pairs that can donate into the metal. So here's what it looks like with the metal complex and all 6 of those iodines there. Now, unlike before with a sigma-only donor, now the metal XY, XZ, and YZ orbitals can interact with the p orbitals on the iodine. So those, the XY, XZ, and YZ, are those 3 lower T2G orbitals. And as we can see, the p orbitals on this iodine actually line up, whereas the sigma donors didn't before. And because those are bonding pi orbitals and those are full of electrons, what happens is those move closer together, it clashes with the electron density. And what we see is we see those T2G orbitals rising in energy. Now note that just one of these effects might only raise one of those 3 T2G orbitals, but because we have 6 of those iodines all around and each of them have 2 different p orbitals that can, clash, we have all 3 of those rising at the same time and equally. So that results in net destabilization, raising that T2G orbital. Now things get stabilized when we have pi acceptors. Here's an example of a pi acceptor, this carbonyl, and here's the metal with 6 carbonyls around it. Here's again that metal and its XY orbital as we're looking at in this example. And this time, instead of having filled pi orbitals, we have these antibonding pi star orbitals. Now these can accept electron density. So instead of destabilizing it, when these come together, those can actually accept electron density from the metal, and that causes those T2G orbitals to get lower, as you can see here. And again, because we have 6 of them all around and all of that interaction together, those 3 are going to move all together at the same amount. So that results in stabilization, lowering that T2G orbital. So what we can do now is we can tie together what we talked about with energy and our colors along with our orbital interactions. We can take a look at what happens. So our sigma only donors in the middle, our pi donors on the left, and we're going to take a look at what happens when that pi donor interacts with that metal. We see again that because of that destabilization, it moves that T2G up. And if we tie in what we learned earlier, right, that's going to decrease the energy gap and increase that wavelength. So in the upper right-hand corner, we see that the arrow is pointing to a higher wavelength, and we also see that that's changing the color from that purple to that green color. Now we can take a look at the same thing, reset the little color wheel, take a look at the same thing with the pi acceptors. Similarly, when we have this interaction, right, it stabilizes because it can accept electrons from the metal orbitals and lower those T2G orbitals. That increases that energy again and decreases the wavelength. So we see that it now is absorbing purple and it looks yellow. So this is one way to think about our spectrochemical series. Where on the left, we have our pi donors that have extra lone pairs that are in pi orbitals that can donate and decrease that energy, right, and change the color. In the middle, we have our sigma only donors, and on the right, we have our pi acceptors, which can lower those T2G orbitals, increase the energy, and decrease that wavelength. Thank you all for listening. I hope you learned a little bit about orbital interactions and how that affects color in d-orbital splitting.